First of all, thank you for listening to this talk about the inside of the Overpass API. We will start with the big picture, then learn what makes a request fast or slow in general, and finally inspect the crucial details of a single query statement. The public instance on overpass-api.de sees each day between 4,000 and 6,000 unique IP addresses. It receives between 150,000 and 250,000 requests each day and answers them with 10 to 30 GB of data per day. The real challenge is that requests differ extremely in size and by their nature. The vast majority of people makes very small requests and expects immediate answers. The few that do large requests shall benefit from the majority of the performance of the Overpass API, but leave enough resources to satisfy later on small requests. So how can we share resources over 7 orders of magnitude fairly? First, we associate to each request a maximum allowed runtime in seconds. The server keeps track of free time units not used by running requests and accepts a new request only if it reserves at most half of the remaining free time units. I will explain the whole mechanism with an example. In idle state, the server has 240,000 free time units. Now a client asks for a request with a timeout of 180 seconds. The server accepts this request and reduces its free time units by 180 units. Now another client asks for a request with a timeout of 86,400 seconds, and the server accepts that request and reduces its time units accordingly further. Now a second request with again a timeout of 86,400 seconds is asked for, but the server denies this request because this 86,400 seconds are more than half of the remaining free time units. The amount of remaining free time units remains unchanged. Now again a small request is asked for. The server accepts this request and adapts the number of free time units accordingly. To sum up, requests with a short allowed runtime get high priority. Requests with a long allowed runtime get low priority. This strategy has been successful enough to be able to accept all requests since June 2012 that have a standard or small timeout. We now investigate how a request is processed. To find the bottleneck of the server, we investigate the Moonin diagrams. While the processors are almost always idle, the disk often peaks near 100% usage. So we only need to care about disk activity. Thus we count in the following only the seconds spent reading the disk. We take a simple example and vary the verbosity of the output. The two statements of the request are executed one after another. The query statement always only collects concise information about the objects found. This so-called skeleton consists for nodes only of the node ID and its coordinates. The out statement takes extra time to collect the tags of the found objects. Now we output only the skeleton of the found objects. In this case, the out statement takes no extra time because all the information is already known. By contrast, if we output also meta information, the whole request is served even slower. This is because the meta information is quite large and it takes a really lot of time to collect it from the hard disk. To sum up, every statement takes its own small or large amount of disk time, and internally the Overpass API only stores skeletons. For that reason, every more verbose output statement will take more runtime. We now further break down where this runtime comes from. We discuss for this purpose the pipeline of the most important statement, the query statement. The query statement applies its conditionals not one after another, but once at all, and goes with all conditionals simultaneously through a pipeline of 9 stations. In particular, this means that opposed to statements, more conditionals are faster than few conditionals. Let us walk again through our example. The first thing to do is to look up which nodes have the given name. We find one result. To retrieve the full node skeleton object from the database, we first need to look up its index to have a chance to find it at all. This lookup takes on its own a unit of disk time. Now we can read the node skeleton object from the database within only 1 unit of disk time. This completes our query. We now compare this query with one result with a query with several 10,000 results. We look up the IDs of all objects having this tag within only 1 unit of disk time, although these are 80,000 objects. But looking up for each object ID the corresponding index of the object now takes insanely 80,000 units of disk time. To fetch all the skeletons now takes fewer time than looking up the indices, but still 30,000 units of disk time because the objects are geographically distributed all over the world. Altogether, the query works, but it is really slow. Now compare what happens if we restrict our search to a small bounding box. The collection of the IDs of potential results still takes only 1 unit of disk time, but we can now derive the index to search at directly from the bounding box immediately without any use of disk time. And the small index allows to fetch all results within 1 unit of disk time. So the complete query only takes 2 units of disk time compared to 110,000 units of disk time for the same query without a small bounding box. To complete our analysis, we again get back to our query with only one result and add a really large bounding box to the conditionals. Obtaining the ID of the one result only takes 1 unit of disk time, and the index to search at can still be derived from the bounding box with no unit of disk time. But searching at this many index positions for the node skeleton takes 3000 units of disk time. Though this query with a large bounding box is much slower than the same query would have been without a bounding box. To take a resume of the whole talk, be bold, the server cares for large queries. Select carefully the output mode to get the fastest possible result. Add all available information as search conditionals to make the query as fast as possible. I thank you for your attention.